Welcome to the class. So we are at the topic of basics of thermodynamics and Brayton cycle. Within that we had completed already the basics of thermodynamics and we started with Brayton cycle. We saw what are the processes which involve to compose the Brayton cycle. Then we saw also the heat and work interaction in the Brayton cycle. Obviously we are considering at this moment ideal air standard cycle. So we first studied in last class about the Brayton cycle, how to write its PV diagram, TS diagram, HS diagram, and then we saw its heat and work interaction. So in today's class we are going to discuss how to find out the different corner properties, something like this. We are having Brayton cycle here. So in the Brayton cycle we see that there are 1, 2, 3 and 4 as corners. So we feel that we should know how are the properties at all the 4 corners. So for that we will proceed for the calculation. So now let us see that what is known to us. From the design perspective we would be known with Rp, which is a pressure ratio, which is known as P2 by P1, and then we would know that we are working with gas which is suppose air or helium or any other gas CO2. Then we know its gamma. Then we know Rp, we know gamma, and then from the application point of view we would know the inlet to the compressor which is T1, and we would also know which is the maximum bearable temperature to the system what we are considering. So this 1, 2, 3 and 4 is our Brayton cycle. In that we know T1 here and we know T3 here, and we also know what is Rp here. So knowing these quantities we should find out what are the other quantities at other corners. So in the process 1 to 2, so what is happening? We should know T2 and P2. So but we know P2 by P1 is equal to Rp, but right hand side Rp is known to us. That's why P2 is equal to P1 into Rp. So now we know Rp. Then we should know T2. For that we know the formula from isentropic relations. T2 by T1 is equal to P2 by P1 bracket raised to gamma minus 1 upon gamma. So this is isentropic relation. We can derive it from the point of view that in the isentropic process we have PV raised to gamma is equal to constant. So if PV raised to gamma is equal to constant, we have P upon rho raised to gamma is equal to constant. Then we can replace rho by T using the relation P is equal to rho RT. Then we can get the formula T2 by T1 is equal to P2 by P1 bracket raised to gamma minus 1 upon gamma. But what is P2 by P1? It is Rp. So Rp raised to gamma minus 1 upon gamma. So this gives us T2 which is equal to T1 into Rp raised to gamma minus 1 upon gamma. We should keep one point to be noted that Rp is the pressure ratio of the cycle and it is P2 by P1. P2 is the pressure after compression, P1 is the pressure at the inlet of the compressor. So P2 is always greater than P1, so Rp is greater than 1. Since Rp is greater than 1, P2 is higher. Further, Rp is greater than 1, so T2 will be higher than T1. Then at point 3, basically now we know that P1 and T1 are known to us, but we found out P2 and we found out T2. Now we have to find out P3 and T3, but T3 is known. There would be one more thing which sometimes it would be given. How would be T3 is known to us? T3 is the temperature which is a maximum temperature of the cycle, and that temperature is experienced in the combustion chamber, and hence it would be experienced by the high pressure side of the turbine or high pressure turbine. But turbine is a rotary element. We have seen it's a turbo machine. So in the rotary application of its operation of its, if we expose it to high temperature, it will get damaged quickly. So for that there is an upper limit for temperature which it can get exposed to. So for that all fact, the materials which are used to design the turbine blades will define the maximum temperature at the entry to the turbine. So Tmax is known to us from that material perspective. There is one more way of saying that there is a quantity which is design quantity which is T3 by T1, which is rather Tmax by Tmin. Temperature 1 is at the inlet to the compressor, and at the inlet to the compressor we know that T1 is the temperature. So that is the minimum temperature in the cycle. So this is Tmin, and then this, if we extend, then this is Tmax. So this is Tmin and Tmax, they are known to us, and that we will call it as beta in the present course of ours. So we would either know beta or directly know T3. There is one more perspective that we would be knowing is amount of heat added, which is Qin. That is also known to you. So if Qin is known, we know the formula Qin is equal to Cp into T3 minus T2. Then in that case T3 is equal to T2 plus Q upon Cp, or Qin upon Cp. This Qin is kilojoule per kg. That is how we can know T3. Or if other way we know beta, then T3 is equal to beta into T2. So this is how we can find out T3. But for P3, we know P3 is equal to P2 is equal to P1 into Rp. Process 2 to 3 is a isobaric process. So pressure is constant. So P2 is equal to P3. One more point to be thought over here, how to find out Qin if it is not given to us. Qin is the amount of heat added in the process of combustion. Combustion is done between the fuel which we are going to add and with the air which we are supplying at the inlet to the combustion chamber. So there is one thing which is called as QCV, which is calorific value of the fuel. Calorific value of the fuel. It is amount of energy liberated if we burn 1 kg of fuel. So it is given in kilojoule per kg. So we can find out QCV is equal to mass of fuel into, we can say that Qin is equal to mass of fuel into QCV. But we have to keep a point in mind that in our present cycle we call it as air standard Brayton cycle. We are considering everywhere air as the working medium. So mass of fuel will not come anywhere in calculation except if required for calculation of Qin. That's how we know now T3 and we know P3. And how to find out our next element, which is 4. So for 4 again we know that P4 is equal to P1. So this is known to us. There is one more thing to be remembered that P2 is equal to Pmax, and also P3 is also equal to Pmax. So P1 and P4 is equal to Pmin. That is the minimum pressure is here, and this is Pmin, and then this is Pmax, maximum cycle pressure. Then we have to find out what is T4. So how to find out T4? So to find out T4 we will use again the formula which is P3 by P4 bracket raised to gamma minus 1 upon gamma is equal to T3 by T4. So T4 is equal to T3 into 1 upon P3 by P4 bracket raised to gamma minus 1 upon gamma bracket complete. But what is P3 by P4? P3 by P4 is Rp. So T4 is equal to T3 upon Rp bracket raised to gamma minus 1 upon gamma. So again Rp is more than 1. So this number is more than 1 in the denominator, that will get divided by T3. So you get T4 which is lesser than T3. So we will keep these formulas in mind for our further calculation. Since now we know everything, we are given with, as I said, we are given with P1 and T1. So P1 and T1 are already known to us in this corner. We are also given with Rp. So using that Rp we found out what is the value of P2 and what is the value of T2. So we know everything at corner 2 also. Knowing Qn or knowing T3 or knowing beta, we found out how to find out T3, and then P2 is equal to P3. So we found out P3 also. Then we found out what is P4 and what is T4. So this is the procedure for calculation in case of the Brayton cycle. But once this is done, we will do the next calculation, which is for the efficiency calculation of the cycle. So efficiency, which is thermal efficiency of the cycle. What is thermal efficiency of the cycle? We know that thermal efficiency is 1 minus Q out upon Q in. That is heat lost divided by heat input, which is this ratio is subtracted from 1. So thermal efficiency, we know the formulas for heat interaction, so we can find out. So from the Brayton cycle, if you see the Brayton cycle over here, then we know that this is Q in and this is Q out. So Q in is equal to Cp into T3 minus T2, Q out is equal to Cp into T4 minus T1. So knowing this, we can calculate Cp into T4 minus T1 divided by Cp into T3 minus T2. This is one of the formulas for finding out heat efficiency of the cycle. But there is one more way we can write efficiency is equal to W net upon Q in. This is other way to write the formula. But what this formula is going to lead to us. So this formula is going to lead us. What is W net? W net for us is equal to W turbine minus W compressor. Again, if we go back and see Brayton cycle, then turbine work is Cp into T3 minus T4 and compressor work is Cp into T2 minus T1. So W net is equal to this, but we can rearrange these terms and then we can say Cp to be common, then we have T3 minus T4 minus T2 plus T1. So having said this, we get W net is equal to Cp into, we will rearrange the terms, we will say T3 minus T2. We are taking this and this together. Then we can take other terms together, which is minus, we will say T4 minus T1. But this W net can again be said to be T3 minus T2 into Cp minus Cp into T4 minus T1, which was practically Q in minus Q out. And this is what the left hand side formula has already given us. We will remember this formula, which is Cp into T3 minus T4 minus T2 plus T1 as W net formula, since we would need to calculate one more expression in the downline. Then what would happen? We know now there are few things which are known to us. So among those, 1 minus Cp, Cp get cancelled. So we don't have to mention Cp now. So we have T4 minus T1. But what is T4? From this we know the formula for T4 here, and then we should know also the formula for T2 which would be required. So we will write down that formula for T4, which was T3 divided by Rp raised to gamma minus 1 upon gamma minus T1. And similarly we have T3 minus Rp bracket raised to gamma minus 1 into T1. So this is the formula for T2, this is the formula for T4. So thermal efficiency is equal to 1 minus T3 minus T1 into Rp bracket raised to gamma minus 1 upon gamma, and this would get divided by Rp bracket raised to gamma minus 1 upon gamma divided by T3 minus T1 into Rp bracket raised to gamma minus 1 upon gamma. So we can see that this bracket and this bracket would get cancelled. So thermal efficiency of Brayton cycle is 1 minus 1 upon Rp raised to gamma minus 1 upon gamma. So this is the final expression for finding out thermal efficiency of the Brayton cycle. Now we can understand some aspects over here. What is that? Thermal efficiency here increases with increase in Rp. So if we increase the pressure ratio of the cycle, then denominator increases. So this 1 upon this number will decrease. So you will get more thermal efficiency. So it is expected to work at higher pressure ratio to get higher efficiency for Brayton cycle. So this is the formula for Brayton cycle. So now we will go for the next derivation, which is for the work ratio. So this formula, once it is derived, we have to find out next performance parameter for the Brayton cycle, and that next performance parameter is work ratio. I will denote RW, which is work ratio, and work ratio is, we have said that W net upon Wt, which is net work upon turbine work, but we have found out what is net work. So RW, what is net work? Cp into T3 minus T2, which is turbine, T3 minus T4, which is turbine work, minus Cp into T2 minus T1, which is compressor work, divided by Cp into T3 minus T4, which is turbine work. So Rw can be written, we can split this denominator for two numbers, and then we can get 1 minus Cp into T2 minus T1 divided by Cp into T3 minus T4. Cp would get cancelled, and then we get Rw is equal to 1 minus, then T2. T2 can be replaced as T1 into Rp bracket raised to gamma minus 1 upon gamma minus T1 divided by T3. T4 again can be replaced as T3 divided by Rp raised to gamma minus 1 upon gamma. Then Rw, which is a work ratio, is 1 minus, we can take T1 common from the numerator, we can take T3 common from the denominator. So it is Rp bracket raised to gamma minus 1 upon gamma minus 1 divided by, again we can write Rp bracket raised to gamma minus 1 upon gamma minus 1, but we will have upon Rp raised to gamma minus 1 upon gamma. But then this bracket and this bracket would get cancelled. So Rw is equal to 1 minus, we have Rp, this will go in the top, Rp bracket raised to gamma minus 1 upon gamma divided by, we can write this T1 by T3 as 1 upon T3 by T1. So 1 minus Rp bracket raised to gamma minus 1 upon gamma divided by beta. So this is the derivation for work ratio. So if we know what is the pressure ratio or operating pressure ratio for the cycle, which is Brayton cycle, and then if we know what is T max upon T min for the Brayton cycle, which is beta temperature ratio for the maximum and minimum, we can find out work ratio for the Brayton cycle. Now what is the impact? Now we will consider two cases for drawing the TS diagram. In one case we will feel that beta is constant, and if we vary Rp, what will happen to Rw, and in other case we will feel that if Rp is constant and if we vary beta, what will happen to the work ratio. Then we can draw TS diagram for these two facts. So let us consider a fact that we are having constant beta. So if beta is constant, then we will mark, we will say that this is T min and this is T max. So this is maximum temperature, which is T3, and this is minimum temperature, which is T1. So these are known to us. Now we initially compress from here to here, then we get T2. This is 1, this is, I will say, 2 dash, and I can go from here to here, and then I can come back and my cycle is done. So this is for 1 beta. So now I will draw next cycle for the same beta but with increased Rp. So I can go from here to 2 double dash, but now my beta is same, so I cannot go more than this. So I will have to come back from here. So it is evident from this diagram that here in the first case, we had lower turbine outlet temperature and much more turbine, we have lower compressor outlet temperature and higher turbine inlet temperature. So for that what we can get is higher work ratio. Okay. So we if have for the same beta, so if beta is constant and if we increase Rp, beta is constant, if we increase Rp, then what would happen? Rw decreases, which is evident from in this diagram. So we are increasing Rp. Instead of 2 dash we went to 2 double dash, and since we went to 2 double dash, we have problem in that we have increased compressor work input, but in that context not much turbine work has been increased, so work ratio has decreased. So next is, if I have constant Rp and if I vary beta, now I am going to vary beta, so but my Rp is constant. So now I will write this as 1 and this as other. This is P min and this is P max. So this is constant for me. So I went from 1 to 2 over here, and then I can stop here. This is my T max, and then I come back. This is my 1 cycle. But instead of this fact, for the same pressure ratio, instead of stopping here at 3 dash, I can stop over here, which is 3 double dash. Then I can get this as my turbine work output. So we can see that if we are having beta increased for same Rp, so Rp, this is temperature and entropy, if Rp is equal to constant and if we have beta increased, then we see that Rw increases. Rw increases. So these are two major points which we should remember. So now as we can see, we have derived two relations. First relation what we derived was for thermal efficiency of Brayton cycle, and next relation what we derived was for work ratio of Brayton cycle. We had to remember one point over here, that the work ratio what we have made derivation for in this class is more important when we will get introduction to the non-ideal cycles. So in present case we have turbine and compressors as ideal turbine and ideal compressor, but what would happen is turbine and compressor, their efficiency would not be 100%, and if their efficiencies are not 100%, then work ratio is an important parameter to compare. Problem is this: if I want to compare two cycles which are operating at different pressure ratios, then how can I compare this? That is where, if two cycles, Brayton cycles have two Brayton cycle based plants have same pressure ratio, then thermal efficiency can be helpful for us to compare. The cycle which has higher thermal efficiency is a better plant. But if we have two different pressure ratios, then thermal efficiency won't be directly useful. In that case we have to compare with work ratio, and then we can define the cycle to be good which is having higher work ratio, since higher work ratio means the cycle is insensitive or less sensitive to the component efficiencies that are turbine efficiency and compressor efficiency. So this is what we have to discuss. The next point to talk over here is optimum work output. Condition. What we have seen till time is that we can find out W net, so which is work output. So here we practically means optimum condition for W net, when W net will be maximum. What is the condition at which W net will be maximum? So that condition we have to find out. So let us start for that condition. So for that we first have to write down what is W net. W net is equal to Wt minus Wc. So W net is equal to Cp into T3 minus T4 minus Cp into T2 minus T1. So then we can say W net is equal to Cp, we can take it common, then T3 minus T4 minus T2 minus T1. We can do one thing over here, that we can use the formulas for T4 and T2 to replace their existing form. So W net is equal to Cp into T3 minus T3 upon Rp bracket raised to gamma minus 1 upon gamma minus T1 into Rp bracket raised to gamma minus 1 upon gamma. We have plus, here we have plus T1. So it's like this. So having said this, we can write Cp into this bracket, but in this bracket we will take T1 as common. So T1, so T3 by T1 minus T3 by T1 into 1 upon Rp bracket raised to gamma minus 1 upon gamma minus Rp bracket raised to gamma minus 1 upon gamma plus 1. So this is what we have arrived at. Now we will use the term which we had already used, saying that but what we know is T3 by T1 as beta, which is T max upon T min. This is the design constraint. So once this constraint is known to us, we can write W net is equal to Cp into T1, then beta minus beta upon Rp bracket raised to gamma minus 1 upon gamma minus Rp bracket raised to gamma minus 1 upon gamma plus 1. Now our objective is to find out when W net can be maximum. So let us make an assumption for the finding out derivation, and that assumption is Cp is known, T1 is known, and beta is known, and gamma is known. So these are known quantities. So since they are known quantities, this expression will have these all quantities to be constant. So Cp into T1 is constant, beta is constant, and then gamma is constant. Then W net practically is function of only Rp. So let us find out, and then we need to write, since it is only function of Rp, I can differentiate with respect to d by drp of W net, and this can be then we can use this term, and then we have 4 terms here, 1, 2, 3 and 4. Everything will get multiplied by Cpt1, but Cpt1 is a constant, so we need not worry about it. So that constant will appear as Cpt1 over here. Then beta is not function of Rp, then that is 0 minus this beta is as it is, and then we will have this term can be differentiated and written as minus gamma minus 1 upon gamma into Rp bracket raised to minus gamma minus 1 upon gamma minus 1. So this is differentiation of second term minus differentiation of third term. So differentiation of third term will be gamma minus 1 upon gamma into Rp bracket raised to gamma minus 1 upon gamma minus 1. Then last term is 1, for which differential will become 0. But our job is to find out the condition for maximum W net. So this Rp condition would lead to maximum W net, so this differential will be 0. Having said this differential to be 0, we can make use of, I will rub this and I can use this part, and then this differential can be made to 0, and then Cpt1 can be divided since it is a non-zero number. Basically then we have only 2 terms to get the W net condition, and those 2 terms would lead to, if we rearrange these 2 terms, we will get that Cp, that T1 would go, and then we would have this gamma minus 1 upon gamma would also go, and then we can rearrange the ratios, and then we get beta is equal to Rp bracket raised to 2 upon gamma minus 1 upon gamma. So Rp raised to gamma minus 1 upon gamma is equal to square root of beta. This is the condition for W net to be maximum. Okay, so we will go to the next slide and we will write down the condition for W net to be W max if we have Rp raised to gamma minus 1 upon gamma is square root of beta. But what is this Rp raised to gamma minus 1 upon gamma? We are trying to find out what does this condition thermodynamically means to us. We know Rp is equal to T2 by T1 bracket raised to gamma minus 1 upon gamma, but beta is equal to Rp is equal to P2 by P1 bracket raised to gamma minus 1 upon gamma, and then we have square root of T3 by T1. But what is P2 by P1 bracket raised to gamma minus 1 upon gamma? So this is equal to T2 by T1, and then it is equal to square root of T3 by T1. So what we can get over here is equal to T2 is equal to square root of T3 into T1. So basically T2 is equal to square root of T max into T mean. But there is one more thing. This Rp can also be written as P3 by P4 bracket raised to gamma minus 1 upon gamma, which is again square root of T3 by T1. What is P3 by P1 bracket raised to gamma minus 1 upon gamma? That is T3 by T4, which is square root of T3 by T1. So what we get out here is T4 is equal to square root of T3 into T1. So what we get is T4 is equal to T2 is equal to square root of T max upon T min. So at the condition of this, we practically get T4 is equal to T2. What is T4? T4 is temperature at the outlet of the turbine. What is T2? T2 is the temperature at the inlet of the compressor, outlet of the compressor. So temperature at the outlet of the turbine, temperature at the outlet of the compressor, they should be equal. Okay, so this is the constraint. Then what we can see is this. We can draw the TS diagram for this constraint, and then how would it look like? Basically what we can get out here is this. So this is the constraint. This is T1, which is T mean, and this is T max, which is T3, 1, 2, 3, 4, and then T2 is equal to T4. But we have to remember that we are having this constraint under the fact that beta is equal to constant. So we have to remember that we are frozen to have this T1 and this T3. Among these we get, if we vary pressure ratio, then what would happen? We can have lower pressure ratio. So in case of lower pressure ratio, I will have T2 dash, and then I can go from here, and then I will end up here. Then what is happening in this case is that we are having more heat rejection. More heat rejection leads to lower W net. Okay, there is loss. Further, we need to go to T2 double dash for the same bit, and then this would lead to very large compressor work output. So one stage we have very large compressor work output, and in the other case we have large heat rejection. So these two constraints lead us to the fact that W net would not be maximum, and for maximum W net we need T2 is equal to T4. So this is how we have derived three relations in today's class. First relation was about thermal efficiency of the cycle, where we saw that thermal efficiency depends upon pressure ratio of the cycle. Then second derivation was about work ratio of the cycle. We saw that work ratio depends upon beta and pressure ratio of the cycle, and third derivation was on W net maximum condition, and we saw that compressor outlet temperature and turbine outlet temperature, they should be same if we want to have the maximum work output condition. Thank you.